Hello and welcome to this video on momentum. Specifically today we're going to be talking about collisions and conservation of momentum. Now, at this point you've all done the lab, you've had carts collide into each other, and often what you'll have is the first cart collide into the second, and then there is, afterwards, carts are moving. Now, in this case, A stops moving, B starts moving, but you might have a variety of combinations of momentum. The common trend you should see, however, especially in like this scenario here, whereas the carts are the equal mass, if one stops, the velocity of the second will be the same. We refer to this as the conservation of momentum. In a closed system, the total momentum of the system is constant. Key phrases here: closed system, which tells me that there are no external forces acting on the system. Total momentum tells me the momentum of all objects in the system. And constant tells me that my delta P, my change in momentum of that system, should be 0. Delta P equals 0 or P initial equals P final, both are valid ways to say that. The fact that it's also a system means I can define it as is convenient. Unlike with energy, we typically don't want to include the Earth, but any objects that are moving or interacting are typically what we're going to group in our system. If we go back to the first example, in this particular case, the momentum of the A cart is here in red. The momentum of the B cart is here in blue. If they both have a mass of 500 grams or 0.5 kilograms, velocity, typically about 2 meters per second, which gives me a total momentum of 1 kilogram meter per second. The B cart has a velocity of 0, which means its initial momentum is 0. So the total momentum of the system is 1 kilogram meter per second in the positive x direction. After the collision, the momentum of this car here, this A car, is 0, which means the momentum of the B car has to be 1 kilogram meter per second to match. Which means that if the mass is still 0.5, the V would be 2 meters per second to match. If we change the mass so that the mass of cart A is much larger and still have it move at the 2 meters per second, the total momentum is the 2 kilograms meter per second here plus the 0 kilograms meter per second here, gives me a total momentum of 2 kilograms meters per second. If the A cart stops, the momentum of the B car would have to be that 2 kilograms meter per second, which would equal its mass times its velocity, or more accurately, 0.5 times its velocity, which gives me a velocity of 4 meters per second. And again, this is what you should have seen in the lab. The collision here results in the second car moving faster. The energy isn't conserved in this particular case, but the momentum is. Now, momentum is conserved in each direction. We can say that the total momentum is constant, but it's often easier to say that the momentum in the x direction stays constant and the momentum in the y direction stays constant. So if I have this red car and this blue car heading towards each other, each of their individual momentums, once they collide, will combine to make a total momentum like so. But the x values here in red and the y values here in blue don't change. The value for the momentum in the x direction is constant. The value for the momentum in the y direction is constant. It is unchanging. To look at a sample problem really quick. A 500 kilogram car is heading down the road at 15 meters per second when it strikes a 35 kilogram barrel initially at rest. After the collision, the barrel is flying off to the side and the car is heading this way, 28 degrees off the positive x direction at 12 meters per second. What is the velocity of the barrel? That's my ultimate goal. But let's take some steps and go through each of those individually. First, let's calculate the initial momentum over here for everything in both the x and y direction. Then, over here, we're going to go ahead and calculate how much momentum the red truck has in the x and y direction. And then from there, we'll be able to figure out how much more momentum in the x direction, how much more momentum in the y direction the blue barrel should have, so that way it will add up to the initial amount. Step 1, calculate the initial momentum of each object here and how much momentum the red truck has on its own. Go ahead and give it a try on your own. Check back after you're done. Okay, if you've gone through and done the math carefully, you should get that in the x direction, the only thing moving is the red truck. So the blue barrel provides no momentum. V is 0, 0. The mass of the truck is 500 times 15, should give you a total of 7,500 Newton seconds, or kilograms meters per second in the x direction. Neither of these are moving in the y direction, so my total momentum in the y is 0. After that, I go through and then look at the momentum over here. My total momentum is 6,000. I got that from 12 times 500, but it's 6,000 at an angle. How much of that's in the x, how much of that's in the y? Well, sine and cosine will let me break this triangle up. Give me px of 5,297.69 and py of 2,816.83 kilograms meter per second. Now, the total amount of momentum in the x and the total amount of momentum in the y has to add up to the initial value. So my px needs to add up to 7,500. My py needs to add up to 0. So whatever my values are for this blue barrel in the x direction and the y direction, need to make it so that this plus px for the blue barrel adds up to 7,500, and this plus this in red adds up to 0. Go ahead and give that a try on your own and check back after you're done. Okay, once you've gone through and calculated, the difference between the initial and what I had is this 2,202.31 Newton second. This 2,202.31 plus this 5,297.69 will add up to the 7,500, giving me the same amount of momentum that I had. In the y direction, I had 0 momentum up and down originally. So therefore, the blue barrel has to have the same but opposite direction amount of momentum as the truck does to cancel out, add up to 0. Final step now. Calculate the total momentum of the barrel and the velocity it was launched at. Finding the total momentum of the barrel is just going back to triangles. A squared plus b squared equals c squared will give you the total momentum. So this side is the 2202.31. This is 2816.83. A squared plus b squared equals c squared gives me a 3,575.57 Newton seconds. Remember, if you did not calculate the angle, that is incorrect. In this case, 51.98 degrees below the x-axis in the negative x direction, however you want to phrase that. Calculating the velocity, well, momentum is just mass times velocity. My mass, in this case, is 35. My momentum is the 3,575.57, giving me a final velocity of 102.16 meters per second. Video game physics at its finest right there. That's almost 250 miles per hour, not something we're typically going to see. The general idea, the principle, the simple calculation at this point is all that the initial momentum will equal the final momentum. So if you take all the parts you had originally, add up all their momentums, and take all the parts you had moving at the end and add up all their momentums, the value should be the same in the x, y, and even if we ever dealt with it, the z direction. Conservation of momentum in a nutshell. Anyways, thanks for watching. Have a good one.